Okay, we are back again to the part of the labs of the day. So thank you everybody for joining us again, and Aurora is all yours.
All right, great, thank you. So to start, I wanted to finish up what we were doing yesterday because we had a little sticking point where the spectrum from HARPS couldn't be downloaded unless you had an ESO account. So I've put that spectrum into my GitHub account, and that can be downloaded. So if you look in the workshop notes, the link for the GitHub page, I will actually share it with Esteban so he can share it with everybody. But it's also in the GitHub page. Oh, sorry, it's also in the worksheet. And I'll just show you what that looks like. Let me share my screen. Okay. So this is the GitHub page that should be linked in that worksheet. And there's a bunch of data there. So here, this is the HARPS file that I added yesterday that we'll be looking at. And the rest of the data are the raw data from an observing run that I did on an instrument called iShell. So iShell is a near infrared high resolution. So it has a resolution of about 75,000 spectrograph, and it observes in the K band mostly. And so for the second part of the lab, we'll be working with some of this data. But for now, if people who want to follow along can download this HARPS file, then we'll finish up the lab from yesterday first. Okay, and I'll be using again the same worksheet from yesterday since we'll be continuing from yesterday. So I will share a link for that. So if you weren't here yesterday, here is the link. Okay, so great. Hopefully you have the link and you can open up your collaboratory notebook from yesterday, or you can create a new collaboratory notebook. In the workshop link, I'll share my screen again. Great. In our workshop sheet, we went through the examples yesterday about the Carmenes data. And so the two Carmenes data examples are here. And then I just started the example that I want you guys to all work through. And this is going to be for the HARPS data. So you can use kind of the same type of code where you upload the file, choose the file. So now you'll be choosing this file that you hopefully were able to download from my GitHub page, open the file. And then what I would like everybody to try to do on their own following this example is to try to plot the optical spectrum of the same WASP-76 star. And the reason that I want you to plot a second spectrum of the same star is that just to kind of try to figure out on your own how the data is stored. So for each pipeline, how we talked about today, the data has been presented in different levels of data reduction. So the data today might be at a different stage. The data that we're using today might be at a different stage than the data yesterday. And the data also can be stored in different formats. So I briefly showed you yesterday that in the HARPS data, most of the data is stored in the first fifth extension, whereas in the Carmenes data, we had to look in the fourth extension. So I just want you to kind of play around with this HARPS file and see if you can figure out where the flux data is stored, where the wavelength data is stored, to plot that and to compare it to the WAS-76 spectrum from Carmenes. So I'm going to give people, I don't want to take up too much time since we also have to do the other lab today. But I'm going to stop sharing my screen and maybe give people 10 minutes to do that. So I'll have my camera on turned off and my mic on mute, but I'll be here. So if you do have questions about how to get this working, let me know and I'll come back. And then in 10 minutes, I will show you how I did the plotting. And then we'll move on to the second part of the workshop today. Okay. Okay, it's not a big deal if you haven't finished, but I thought that I would come back and kind of walk you through what I was hoping to do and what hopefully you were able to do with the spectra. All right, so let me share my screen. Okay, great. So the kind of annoying thing about the co-laboratory is you have to re-upload things every time you sign back on. So I just did that and I've re-uploaded everything. So now I'm working with the HARPS data. So I've uploaded the file that is listed in the GitHub page onto Collaboratory. And I've opened it. And now I'm kind of looking around and seeing what there is. So yesterday I briefly opened the header and we kind of looked at that. And then we kind of ran out of time at this point. So now instead of looking at the 0th data extension, I'm looking at the first data extension where often the reduced table data is that's where it is. So now I'm printing out the header, and you can see in the header, it gives me a lot of information. So in the Carmena's data, we saw that in the first extension, only the spectrum data was there. And then we had to look all the way to the 4th data extension to get the wavelength. You can see here in the HARPS, we have the wavelength data, the flux data, and the uncertainty all in this header. And it gives us a bit more information. So it tells us, remember for the Carmenas, it didn't tell us what the units were for the wavelength, so we just kind of had to guess. But here it tells us that the units, where did it go? Oh, here. T unit 1 is in angstroms. And then it tells us that the spectrum, T unit 2, the units are in ADU, which is basically counts. So it's just counts from the extracted spectrum. Okay, so we have lots of information. So now let's try to plot up our spectrum. So I'm going to not comment that and comment this. And let's just try to see what the shape of this is. So let's print out the length of the wavelength array. Okay, it has a length of 1, so it's just a single data. Let's see what it looks like. Okay, so it looks like it's an array, but the array in the array is just the whole thing. But let's check that. So let's see what the 0th entry looks like. Okay, yes. So the 0th entry of the array is huge. It has 313,000 data points. So it seems to me that basically they put an array of length 1 into this data point, so it doesn't really mean anything. But then the entire, it's not like in Carmena's where we had the arrays that all had each order saved as an individual array. It seems to me, by looking at this, that they've already combined all of the orders into a single order. But we can check that by plotting. Okay, so let's now try to plot this. Wavelength. And then remember, we have to do the 0 thing. And then we have to plot flux. And for some reason, the array is stored as the 0th entry. But let's see what that gives us. Okay, great. Here is our spectrum. And yeah, so now you can see for sure that It's a single array, so that means that they've already combined all of the orders in the spectrum that they give you. And it goes from about 3,500 angstroms all the way to about 7,000 angstroms. So now let's compare what we see for the spectrum of WAF-76 with Carmenas to the spectrum of WAF-76 with HARPS. Okay, so remember 3,500 angstroms to 7,000 angstroms. So here we go only from about 5,000 angstroms to just over 1,000 angstroms. And so you can see that Carmenas has a more red wavelength coverage. It goes much farther in the red. So HARPS stops here, whereas Carmenas stops, Carmenas is all the way out here. So let's plot them on the same axis. I'm just going to copy the code. And we have completely different normalizations, so I'm just going to divide everything by its average so you can see what it looks like. So that they'll be on the same plot. I think I need to import NumPy for this. Great. Okay, so I'm just taking the flux and dividing it by the average flux so that it'll kind of look the same as here. We'll take our flux and divide it by the average flux. All right, let's see. And I'm going to make all of these a different color. And all of these another color. Oh, okay. So here is our, oh, I have to divide, sorry. I see I have to divide by the nan mean. If there's not a number, sometimes you get spaces like this. Okay, so now you can see better. There's a lot of noise in the near infrared in the Carmenas spectrum, but the wavelength coverage of HARPS goes much bluer than the wavelength coverage of Carmenas. And I'm going to make both of them a bit transparent so you can see them at the same time. So to make it transparent, I can use the alpha parameter. And that makes it about 50% transparent. And also, I'm just going to zoom in on the y-axis. So I can set the y limit to go from minus 30 to 30. We'll see if that looks nice. Okay, great. That looks much better. Maybe even zoom in a bit more. All right, here are our two spectra. And you can see how here we have HARPS, which goes from 3,500 to 7,000. And here we have Carmenas, which goes from 5,000 to 10,000 angstroms. And if we look closely, you can probably see that some of the features are the same. So I can even zoom in a bit more. And hopefully we'll see that they have some overlapping features. Great, yeah, so we can see like a feature here that looks the same and some other features that look the same. So on your own time, you're welcome to play with this more and try to see how the overlapping features work. But for now, I think that I will quit here since we want to move on to the exercise for today. All right. Let me stop sharing this. And you can look at this and kind of play around with it yourself and let me know if you have other questions. Okay, so then for the rest of today, I'm going to be following the workshop 2, which we're going to be looking at some raw CCD images. And we're not going to be doing any of the reduction ourselves because, like I said, usually there's a pipeline that does it, but we'll be kind of looking at thinking about the steps that you would do in the reduction and kind of thinking about like why the different frames look the way that they do and trying to come up with what that means. So again, all of the data is on the GitHub page, and I put a lot of data there. It's like all of the flat images, a bunch of different spectral exposures, and then a bunch of different dark frames. So if you have limited space, just you're welcome to just download one flat, one spectrum, and one dark. And you can tell the difference because the ones that are flat will say, let me share my screen and I'll show you. Okay, right. So the ones that are flat will have a bunch of numbers, and then it'll say flat, and then this will be the exposure number. So this is flat number 9, 10, 11, 12, 13. So there are a bunch of different flat exposures. The ones that are the spectrum are labeled F name. So that's the source, that's the target. And then we have some dark frames, which are labeled dark here, you can see. So yeah, if you don't want to download them all, just download one exposure of each. So one flat, one spectrum, and one dark.
Excuse me, Aurora, you have a question in the chat.
Okay.
It says, what can we tell at first sight from noticing that the data overlap fits well in the bottom, but not at the top?
Yeah, so from the Carmenas and the HARPS data. Yeah, so this basically just has to do with how, what type of data they're giving us, like how much they've reduced it. Yeah, so you can see that in the original, let me share my screen again. Okay, so this just has to do kind of with both how I plotted it and how much has been reduced. So in the original shape of the Carmenas spectrum, you can see that you're getting a bunch more flux, maybe like around 5,500 angstroms. And this is a combination of the effect of where the star is emitting most of its light and where the detector is sensitive. So because it is a hot star, it is going to be emitting more of its light at bluer wavelengths. And so the reason that we see this kind of trail off here is because the star is just emitting less flux. But this trail off here and the extra trail off down here is because of the way that the CCD is less sensitive on the edges. So this shape here for the HARP spectrum is the same. You have the CCD is less sensitive at the edge orders. And so that's what this shape is given by. Now, because Carmenas gave me all of the orders individually, and I kind of wanted to just plot them on the same axis as HARPS, I just divided them by their average. So that dividing by their average basically takes away the shape. Because I divided each of these orders by its own average, it takes away this full shape. So that's why the shapes don't match up here at all. And also the two detectors have different sensitivities because they have different wavelength regions. So I wouldn't look at just the way that I've plotted this right now. The overall shape of the spectrum doesn't really mean much. We really should be looking at if the features line up. And so if the features line up, that's showing us that the spectra are consistent. This upper continuum, it's not really telling us anything right now, and it's just a factor of how I've plotted it and how where the detectors are sensitive. Hopefully that answers the question. Okay. Great. So hopefully you've all been able to download DS9 successfully, because to answer most of these questions, you're going to have to plot, or you're going to have to look at the images. So I'm just going to show you how some of the basic features of DS9 works before the break. And then in the second part of the class, you can answer some of the questions that I've given to you in the workshop just on your own by looking at all of these calibration images in DS9. So I'll share my screen to show you how some of the basic DS9 features work. And DS9 is often used in, while you're observing or for anything observational, since it's a quick way to look at FITS images. Okay. Okay, so all I've done so far to share this is I double-clicked on one of the FITS files that I had downloaded on my computer, and it opened it in the DS9 application. So DS9 on my system is the one that's configured to open FITS files, but if you need to open it, you can also open DS9 window and say File Open, and then click on the file that you want to open. So I've opened dark 00111. Okay, so some of the basic functions that you're going to need is first, you can see up here in this window, this is the full image, and this cyan kind of blue box is what's actually being displayed here. So it's not displaying the full FITS image. So to zoom out to see it display the full FITS image, you can go to zoom and then zoom fit. Okay, so now you can see the entire CCD image. And this is a dark, so it should look relatively dark, except for with some of these like hot pixels here, which is what it's supposed to look like. So that's great. The other thing that you're going to need for the exercise is to see, okay, here you can see that it says value. So when you scroll your mouse, it is changing the value. And so the value is basically the number of counts in the pixel where your mouse is. So here in this pixel, there's 85 counts. Over here, there's 88 counts. And if I can get my mouse to go on a hot pixel, you'll see a huge number of counts. Yeah, there's like 200 counts if I can get my mouse on the hot pixel. This one. Yeah, 200 counts. Great. And then the other thing that you'll need, so you can also look at the image, and here it lists X and Y. So as I scroll my mouse across, you can see that the X is changing and the Y is changing. So where my mouse position is, this is telling me what the X pixel is of my mouse position and what the Y pixel is of my mouse position. Okay, so then for this image, you don't really need to change much on the scale, but for some of the later images, to actually see the features, you're going to have to change the scale. So you can kind of, if you click scale, you can kind of play around with all of these buttons, but often the Z scale works nice for seeing some of the fainter features. So if I do the Z scale, you can kind of even see there's a little bit of these up and down vertical lines, which are basically the CCD image has kind of a mesh pattern on it, which is showing the difference of the pixels. So you can kind of see that in some places. Yep. So Here's a histogram. You can just kind of play around with it and see what looks nice. Yeah, this one kind of brings out all of the really bright pixels. This one kind of equalizes everything. So just play around with it. And another thing that you can do is if you, actually, I'm not sure how to do this on a PC. I have a Mac. So if I press Command and then hold down Command and drag my mouse around, it changes the scaling for the y-axis. So this can again be useful for bringing out different features. So if I really only care about the bright pixels, I can kind of drag it over here. But if I care about some of the dimmer features, you can drag it over here. And so just play around with that. Yeah, again, on my Mac, I can hold Command and scroll. I can search to see how you do it on a PC, but I'm not sure. And so then some other cool features, you can just, change the color, which always just looks pretty. I think that's all we'll be using today. Some features that you might want to use for another time, if you ever use DS9, you can add grid lines. Okay, that's adding contours. The contours basically take the brightest regions, but it doesn't really do much on a dark frame. So if you want to add contours to your flat frame, that'll look a lot better. So let's get rid of that. Oh. And you can add grid lines. So this kind of helps you to tell, what pixel number you're at and stuff. And also, again, for the dark frame, I don't know what this will do, but you can smooth things. Okay, yeah, it doesn't do much for the dark frame, but it'll look better if you try smoothing things in other frames. And lastly, you can, if you do want to think more about the scale and how to bring out certain features, if you click on scale parameters, if you go to parameters, scale parameters, you can see what pixels are being displayed with the scale that you're looking at now. So you can see I'm really only looking at the very brightest few pixels. Or sorry, I'm looking at, so you can scale the high value. Right now, my high value is set to only be 800, but you can scale it up. So you can see there's some extremely hot pixels. Okay. Great. So that's kind of if. Let me know if you have any questions about DS9, and let me stop sharing. Okay. So then for the rest of the lecture, I guess there's I think there's 10 more minutes, and then we have a break, and then there's another half an hour. So maybe you can start working on some of the questions, then take a break, and then maybe we'll do 15 more minutes of working on questions and take a break, and then I will go over some of the answers in the last 15 minutes and answer any questions that people have. So just to show you in case you don't know what worksheet I'm talking about, just share my screen one more time. Great, okay. So we'll be working with this sheet today, and I kind of just went over some of these basic features, and then I want you to answer these questions on your own. So you can start answering a few of them, and then we'll take a break, finish doing the answers, and then I'll come back and explain what I was hoping that we got out of this. Okay, so I'm going to put my camera off and my microphone on mute again, but I will be here, so if you have questions, just ask me and I will come back and answer. Okay, so we are going to be going on a break in 2 minutes. So I just wanted to make sure that everybody knows what we're doing. Hopefully you were able to locate the worksheet. It's on the same page as the worksheet from yesterday. It's just on the second page of that. And hopefully you were able to get DS9 working and started to look at some of the images. So we're going to be going on a break in about a minute. And then in 15 minutes after that, we'll start the next session. And for the first 15 minutes of that, again, you can continue to work on the questions with the data. And then in the last 15 minutes, I will kind of explain some of the answers to the questions and what I was hoping you would get out of this. And you can ask me any questions that you have about this data.
Yeah, hi, Aurora. I haven't seen any questions yet on the chat. So my guess is that we should go for the 15 minutes break. And maybe this will give some time to the participants to see if they will finish what they were doing. And maybe they will bring up some questions in the meanwhile.
Okay.
Okay, then see you all in 15 minutes. Thank you very much.
Bye.